All right, welcome to gas laws number 4 and 5. And I really am going to put these both together in one video, this shot. Pause as need be. So Joseph Louis Gay-Lussac's law, again using that backbone of kinetic molecular theory in order to come up with this law, Gay-Lussac discovered that if pressure and the number of particles in a container remain constant, there is a direct relationship between pressure and temperature. Very similar to Charles' law. The only difference is that it's pressure divided by temperature instead of volume divided by temperature. Again, this is a linear relationship. If I graph pressure on the y-axis, temperature on the x-axis, the slope is going to be the product of pressure versus temperature, and we call that the proportionality constant K. So we're going to practice this problem here. A gas in a sealed container has a pressure of 125 kPa and a temperature of 30 degrees Celsius. If the pressure in the container is increased to 201, what is the new temperature? Again, I gave you the hint, you've got to change those Celsius to kelvins. Furthermore, we can make a gander of what our answer is going to be by just looking at this data. So if I'm looking here, I go from a pressure of 125 to a pressure of 201, an increase. So I'm going to predict, according to Gay-Lussac's law, that the temperature is also going to increase. Let's see if that's the case. So let's set up our Gay-Lussac's law here. P1 over T1 equals P2 over T2. I'm going to do this right off the bat. I'm going to change my temperatures into kelvins, just like we did with Charles. 273 plus 30.0. So notice here I've got to make sure that I remember I have 1 decimal point for my temperature. So I'm going to have here 303.0 for my initial temperature. And for my final temperature, I can convert back to Celsius if I want to, but I could also leave it in kelvins. So my goal is to get the final temperature. I'm going to start by multiplying both sides by 1 over the second pressure. That is going to isolate T1, but I have to end up taking the reciprocal. So I'll have P1 over P2 T1 equals 1 over T2. And then I can take the reciprocal of both sides, since there's only one expression on both sides. P2 T1 divided by P1 equals T2. There's probably other methods to isolate T2, but that's the one I prefer. There's no right answer to that, however. So initial pressure is the 125 kPa. The initial temperature is 303.0, remembering that decimal place. Excuse me, I wrote down the wrong one. My final pressure is 201, my fault. 201 here. My initial pressure, which is what I should put in the first place, is 125. And now I'm ready to solve for T2. So I'm going to grab my calculator. I'm going to take 201 times the 303.0. I'm going to 3 sig figs here because there's 3 sig figs in 201. So it's going to turn into 60,900. That decimal place that I made sure I put there went away because I'm multiplying and I only have 3 sig figs. Divided by the 125, that'll get me my T2. Down to 3 sig figs again. And my answer here is 487, write that meter, 487 kelvins. Now if I want to go back to Celsius, I subtract the 273 and I find out it is 214 degrees Celsius. I said before that I think my temperature should have increased, and it did, from 30 degrees to 214. So hopefully that is a great example of Gay-Lussac's law. And I'm going to pause here so you can take some more notes on that, and then we'll go on to the combined law. All right, here we are with putting them all together. We're going to put together Boyle's, Charles, Gay-Lussac's law, and it's going to be called the combined gas law. So watch very carefully how I combine these gas laws together to get the combined gas. So here's how we combine them. We know that P1V1 equals P2V2. Well, there is Boyle's law. We know that volume divided by temperature, there's Charles' law. They're all combined together. And we have pressure divided by temperature as Gay-Lussac's law. They're all put together here. And that's how we get the combined gas law. It's all three of those put together. The only item that remains constant in this whole entire process is the number of particles of your gas, or the number of moles remain the same. So let's do a practice problem. So we got a child's toy balloon with a volume of 1.8 liters, 1.8 deciliters cubed. The temperature of the balloon was filled to 220 degrees Celsius. So there's going to be my V1, there's going to be my T1, and we've got a pressure of 1 atm. There's a P1. If the child were to let go of the balloon and it rose to the sky to a pressure of 0.86 atms, there's P2, and the temperature is 80 degrees Celsius, that is going to be T2. What would be the new volume of the balloon? So I'm solving for V2. So here's my combined law. And I want to isolate V2. So I'm going to multiply both sides by the reciprocal of T2 divided by P2. And that's going to allow me to cancel out the second temperature on the right, the second pressure on the right, and I'm left with this expression. P2 times P1 times V1 divided by P2 times T1. Let's change some temperatures to kelvins. My T1 is going to be 220 plus the 273, 493. And my T2 is going to be 273 plus 80, 353. All right, so we're going to shove this all in now. P2 is going to be the 353. The P1 is going to be the 1.0, 2 sig figs there. V1 is going to be the 1.8, 2 sig figs there. T1 is going to be the 493. And now I'm ready to grab my calculator. So my calculator is going to render the result of me doing 353 times 1.0 times 1.8. I'm going to round that part to 2 sig figs to get me 640 to 2 sig figs. And I'm going to divide that by 493. 640 divided by 493 gets me a new pressure of, or new volume, excuse me, of 1.3 with 3 sig fig, or 2 sig figs, 1.3 ATMs. So this one's a kind of a harder one to guess and check by looking. I had a decrease in pressure. If I decrease my pressure, I should have decreased my temperature, which is what happened. But if I decrease my pressure, my volume should have increased, but it didn't. So in this case, the pressure temperature difference has outweighed the pressure volume difference, and I do have a smaller pressure at the end, which makes a lot of sense because as something floats up into the atmosphere, the pressure is less, and so the temperature is less as well. So hopefully that's going to talk you through Gay-Lussac's law and the combined gas law. We got one more to go, folks, and that's ideal gas laws coming up next.